Welcome to chapter 6 on operating systems. Now, as you know that hardware is just a piece of physical device. What makes it usable for people like you and me is what is known as the operating system. What is an operating system? When you switch on the machine for the first time, what you call as a process of bootstrapping, which is to say that on the hard disk of the machine, there's a small, after the ROM gets energized by electricity, some software gets loaded, which is known as the bootstrap loader. The bootstrap loader in turn accesses the hard disk and fetches a program which is known as the operating system. The operating system is fundamentally a supervisory program which is omnipresent, which is something which runs in the system as long as the system is on. When you switch off the operating system, usually you shut down the operating system and then switch off the machine. So an OS is something which always is there. It is there to help you. It makes it easy for you to communicate. There are four primary functions that an operating system performs. One, what you call as the memory management function. Second, what you call as the CPU or the processor management function, or the process management function. The third, which is management and interaction with all the devices which are connected to the computer, known as the device management function. And the last but not the least is the ability to interface with end users, making their life easier. So for example, today we look at an icon and click it, making it so easy for us to interact with the system. This is as opposed to some of the interfaces which we've experienced earlier. Some of us have actually typed in commands which are very cryptic and complex commands to make the machine do things for us. Now you can't expect an average user to do that, so you have user interface design which is very intuitive, very simple for people to operate. So these are the four primary functions of an operating system. Just to recite again: process or processor management, memory management, device management, and user interface. Let's look at each one of them in a little more detail. Let us look at the first function of the operating system, which is the process or processor management. Look at the diagram here. You will notice that the CPU is at the center, like the boss, and around that is the operating system, not physically but conceptually. It's like having a personal assistant around the CPU, the boss. So if you want to meet the boss, and many people actually want to meet the boss simultaneously, it is the PA who actually handles the appointments and ensures that the boss's time is neither wasted nor is it overloaded. And it also ensures that people are not kept waiting outside, for example, to meet the boss. Now, the operating system does pretty much a similar job. So there's just one CPU in the machine, and the time of the CPU is very crucial. And there are multiple job requests A, B, C, D, E, F, G, for example, simultaneously being shot at the CPU. How can the CPU allocate time to all these jobs? And it's the operating system which ensures that there is some mechanism available, either in the form of queue, for example. First job A will be processed and then job B will be processed. It's on a first in, first out kind of a method, and therefore everybody gets a due share of the CPU time based on a sequence. This is typically a mechanism known as batch processing, which was very popular in the earlier days. Now obviously batch processing has a limitation in the sense that the person G who came in the last will have to wait till the end of all the processing of everybody else. And imagine, for example, that if I have a very small letter to print and all the previous ones are huge things, for example, somebody is printing 1 lakh check dividend warrants, somebody is printing salaries of 10,000 employees of the company. If after all of that my one letter will get printed, I will have to perhaps wait the whole day or probably 3 days before the letter gets printed. Now obviously therefore this mechanism is not suitable for current day processing needs, where you need instant service from the device that you are seeking it from. And it is therefore the operating system which provides a different method of communicating with the requesting people. And how does it do it? It does essentially a time sharing. Time sharing is nothing but a round robin mechanism where the CPU's time is sliced into several pieces and one slice is allocated to each user. So the CPU gives attention. It's pretty much like being in a classroom, for example, and then one person stands up and shoots a question and I look at him and answer that question. while the other people are still raising their hands, and I ask them to please wait till I answer the first person's question. Now I answer that question partially and then look at you and answer your question partially, and then go back to the third person and answer his question partially, so on and so forth. And I sort of rotate between the set of people who are continuously asking questions. The same principle is perhaps used here. So the CPU is made to look at job A for some time, then it is switched to job B for some time, and then to job C for some time, and so on, till it finally comes back to job A, B, and C once again. So it cycles between all the users. Every time it switches from A to B, all the content of the program associated with job A is sort of parked. The status where it was processing is maintained and remembered by the system, and then it moves on to job B. At the point where the job B was last stopped, gets loaded, and the processing happens for that time slice for the next set of instructions. So you keep switching across jobs at a rapid pace. By doing it, what it achieves is it achieves processing of every job to some extent in every cycle. The result of which every user gets a feeling that the CPU is actually paying attention to my job. So everybody sort of feels serviced at any point of time. So operating systems provide this feature known as time sharing. And these are two fundamentally different ways of doing it. Therefore, queuing up versus round robin. Round robin obviously is the most popular one which we now practice. So all systems today are actually multitasking systems, can handle multiple tasks in a round robin fashion. The second major function of the operating system, which is managing memory. And as you know, memory is a scarce resource. Memory is where you store information which is being processed right now. You store the programs which are currently operating in the computer at this point of time. And you store data which is moving in and out of the main memory because it's been processed or because it is going to be processed, what you call as in-transit data. So if you were to conceptually draw a diagram to show the various components of memory as they look like, or the pockets of memory that you see, they look like something like this. So A, there is what you call as reserve space, where all the program code which is fundamentally required to interface with various devices which are loaded from the ROM. When you boot up the system, there is a micro-coded program which is inside the ROM, which gets stored in the main memory in what's known as the reserve space. So for example, if I want to print something, what are the interactions required, what are the software required to make that possible to communicate with a printer? Such microcode is available and it is stored in the reserve spaces. The second area, which is the buffer space, which is for in-transit information. So if I've just picked up a sector from the disk and read it into memory, before it goes for further processing, it is stored in buffer. Why? As you know, buffer is required because there are electromagnetic devices and memory works at nanosecond speeds. So to buffer the gap between the speeds, there is a buffer space left. Space for programs. So if you are running an Excel, a Word, and something else, and an email program, so various windows that you've opened, each window that you create is actually nothing but a separate program, and simultaneously all these programs partially reside in the memory, and therefore you need space for programs which are currently running. Then you have space for the data which those programs require. So for example, there is certain data associated with your Excel spreadsheet that is stored in memory again, and if you're typing a letter, then that letter is temporarily stored in the memory till the time you don't save it. So if you have 10 programs, 10 tasks simultaneously in memory, data pertaining to these 10 tasks are simultaneously stored in the space for data. Then you have free space, and free space is allocated. So if your Excel spreadsheet needs more space, it takes up space from the available free pool. And likewise, any other, if your letter expands to 10 pages, then more space is acquired from the main memory and used up. Now, at the top, you have a space where the operating system itself, once you've booted the system, the operating system goes and sits in there, and it acts like a omnipresent software which is continuously monitoring everything that's happening in the system. But interestingly, it is the operating system which manages this allocation and deallocation of space within the RAM. It remembers the partition information about each of those pockets of data that we just saw. So it remembers which is the buffer space, which is the program space, which is the data space, which is the free space, and it does not allow any of these partitions to be mixed up. So you won't, for example, have a mix-up between 10 programs which are working simultaneously, nor the data pertaining to these 10 programs get mixed up. All this becomes the role of an operating system. So the operating system essentially manages partitioning, and it manages allocation and deallocation of space available. Just to give an example, if you close one of your 10 programs, let's say the Word or spreadsheet, what happens to the space which was occupied by your spreadsheet program? What happens to the data occupied pertaining to the spreadsheet program? That gets freed up. So it becomes the operating system's job to deallocate that space and make it available to the common pool, which can subsequently be used when a new program gets loaded or new data wants to occupy more space. Now there's another concept which is associated with memory management, which is very popular now on large systems, servers, and all of those, which is known as virtual memory operating systems. What is virtual memory? Since your RAM is limited in terms of the physical chips that you've installed, how can I infinitely expand my memory? And one way to do it is to occupy your hard disk itself. And some part of your hard disk, if it is called as memory, and if you have a logical grouping of data from your hard disk which can be loaded and unloaded from your RAM, these are known as pages. So you load a page, offload a page, and you continuously keep doing that. It seems to the user that the RAM has expanded, because if there is shortage of space, it stores some information which is not immediately required, and it stores it in a page on the hard disk itself. So now your main RAM is freed up for the data that you want to store more on it. And when you need data which is now lying on the hard disk, for example, as part of your memory, you don't have to remember it. It is the operating system which automatically brings forth that page and allows it for access to the program. Now this is known as virtual memory concept. So to you it appears as if memory is infinite, as large as the hard disk itself. And this is the concept of memory management as a whole. The third major function of the operating system is device management. You have multiple devices, say the printer, the hard disk. Each device needs to be managed effectively. For example, what does it mean to manage a hard disk? When you store data on a hard disk, as you know, there's a notion of a file system. So the hard disk is actually logically split into several files, folders and files, etc. Now a file can be stored at multiple points on the hard disk, spread all across the hard disk. And therefore it's important to know which are the sectors to which this file belongs. So, or rather, this file has been spread over which sectors, and if the file expands, which are the new sectors which got added. So the file system and the index of the file, the FAT as they call it, file allocation table, essentially maintains information about where data about a file is stored or associated with the file is stored, the name of the file and the actual information contained in the file, and on which sectors it is located. So when you want to access, let's say, your letter which you have just typed, part of the letter could be stored on track 1, sector 1, part of the letter could be stored on track 3, sector 15. Now who remembers this? It is the file system which remembers it, because in the file allocation table it says against my letter name, it says these are the sectors which have been allocated for the file. Now when a software wants to access the file, it has to read from the device, and who enables this to be made possible? It is the operating system which has created this file system, because it understands how to access a particular sector from that disk. Therefore, this is what you call as disk management. It is about managing space on the disk effectively. The second major type of device which you interact with is typically a printer. Now in this context, when you refer to an operating system doing device management on the printer, suppose I give a command to print. It is the operating system's duty to find out whether such a device is connected to the machine at all. So it sends a message saying that do you exist and are you ready to communicate? And if the device, such as a printer, if it's ready, it responds back saying that yes, I'm available and I'm ready to print. And the minute it gets that signal, your print command gets executed and it diverts whatever content which you have indicated to print. It sends it through your Word program into the printer for further printing. Now there is a possibility, for example, that your printer is switched off, or the paper gets jammed, or there's an error, there's no paper, for example. The printer sends a signal back to the operating system saying that I am not ready, and it does that. The operating system recognizes that the printer is not ready. It tries and retries again, and then it realizes that it's really not ready, and then gives an error to the user saying that printer not ready, please retry. So these are some of the mechanisms which the operating systems enables. By doing this, it makes life of the user so much more easy. So device management in this sense is about enabling action with the device, ensuring that the communication happens properly, and monitoring that everything is smooth. And in case of error, giving back error messages to the user. There are some other interesting features which some of these operating systems provide. For example, when you have a shared printer, for example, in a work group, so there are 5 people and there's one single printer on the network. All of us shoot a request for printing a letter, a report, or whatever. So depending on a first in, first out mechanism, our output gets queued up. So the activity of queuing up, assigning priorities to the printouts, is something which the operating system can govern. That's an additional feature. Not all operating systems are designed to do it, but you can have operating systems, as you see in Windows, for example, it does it. There are other interesting features. For instance, you have privileges assigned. So for example, I can define, since I am the creator of this document, I do not want anybody else to be allowed to open it, or I might allow them to open and read it but not change it. Now these kind of privileges can be defined. For example, operating systems like Unix allow us to do that, and those are interesting features for security. You have even accounting features. For example, if we have, let's say, multiple people sharing a server, and I actually want to charge each department for the amount of data that they've stored and the amount of space that they've occupied on the server, I can actually do an accounting mechanism. I could even do accounting on the basis of connect time. How many time, for how long did somebody connect? And based on that, I could have a charging mechanism for it. So all these could be features which an operating system can provide. The last but not the least, as I mentioned, is user interface. So it's human-computer interaction, and how can you make it very easy, which is what the operating system addresses. In the earlier days, for example, those of us who have worked on MS-DOS, who have worked on Unix, who have worked on some of the earlier proprietary operating systems, you would remember that you had a character, a command line interface. You would get a symbol, say a greater than symbol, and against that there's a cursor on which you type a command. And against that command, the operating system responds. Either it's an incorrect command or it actually executes a command which you have requested. Now these were known as command line interfaces or character interfaces. Now command line is typically very cryptic, very difficult for lay users to remember a variety of commands. So some of you read a Unix command manual. It's so complex in the sense that every command has hundreds of options. You put a slash and put R, it means something else. And you put a slash and put U, it could mean something else. So a variety of options could be created for the same command, making it so difficult for people to remember. So for technical people, of course, it's a very easy way of typing commands. What came up with the Mac, and that is the Apple computers and the Windows, for example, for the first time, what's known as the graphical user interface, which was a point and click kind of a mechanism. There are icons which are figures which are very easy to understand. So for example, if you want to delete, all that you do is take a file, point to it, press a key and drag it, and drop it into a trash can. So there's a symbol for a trash can, and you drag a file and drop there. It is so intuitive, it's very easy for you to understand, and that makes GUI very popular in today's context. A lot of new operating systems are also providing interfaces which are natural language interfaces. So for example, if there's a blind person who wants to operate a machine, can he just talk to the machine and expect the machine to perform an action? So for example, it could actually select, it says run Microsoft Windows, and it actually executes that. Then it's a great phenomena for the blind people, for example. Personalization is another important aspect of operating systems. Personalization is about making the machine more suitable to my way of looking at things. So I prefer these colors, and I prefer this, for example, screen, which is a default screen, and I prefer these kind of icons here. I feel that this is the type of cursor that I prefer. Now these are examples, trivial examples of personalization, but which was not possible in the character-based interfaces, which are now very popular in the graphical user interfaces. Now, one important aspect of operating systems is the ability to provide programming facilities, and a lot of programming languages exist in the world. I think I would say more than 100 or 150 languages exist, and they have evolved over time. So there's no one type of a language which exists. So at the lowest level, if you see, there is something known as the machine code. Machine code is primarily zeros and ones. It's the digital or the electronic signal which we talk about. That's where the machine operates really. Now machine code is impossible for you and me to code, to write programs on. So therefore people evolved into something known as a short form notation, which was known as the assembly language. For example, I could say add, and the short form for add could be AD 5, 10, which sort of says add the two numbers 5 and 10, and let's say if I put another comma there and say C, which is to say that add 5 and 10 and put it in C. So assembly language is a short form notation. It's near English, but it's sort of cryptic English, which technical people find it very easy to use because it occupies less space in memory, and therefore very suitable for doing programming at a microprocessor level, which has very limited memory available to itself. Now assembly language being near English, how do you convert it back to machine code? Because machine code is what really runs on the system, and therefore you need a software known as assembler which does the conversion. So the short form notation of add, AD, or LD for load actually gets translated into equivalent machine code and then sent to the computer for execution. Over time, people realized that even assembly is too clumsy for people in business, for example. So you needed a near English-like language, and therefore the evolution of what's known as the third generation languages, COBOL being one of the best examples of such a language. So you write a program in COBOL, which essentially tries to describe an entire procedure of doing things, and therefore you find that third generation languages are typically described as procedure-oriented languages. What you do is describe a complete procedure for processing something. And to give an example, if I'm doing a payroll processing, in a COBOL program, typically I'll have to describe the file and the structure of the file and the columns in the file, etc., how the data is stored. And then I have to describe, please open this file, take the first record, read it, and then transfer the data to memory, and take the name of the person, the basic salary, DA, etc. Then you say that calculate the final salary based on the basic DA, HRA, and all of that, and now you print the payslip of employee 1. Having done that, please go back, read another record, take the next record, which could be record 2, and repeat the same processing, so on and so forth. And every time you go back to the next record, please check that it's not the end of the file. If it is the end of the file, close the program and stop the print. So I'm completely describing a fairly complex and looped kind of a programming logic, describing in near English by using commands such as open, read, move, calculate or compute, and print, for example. So these are pure English language verbs which are used to describe the actions which you expect the software to execute or the machine to execute. Therefore, third generation languages are procedural languages. They describe procedures. Now, once you've written a language in this form, obviously you need to convert it back to machine code. So when you write that English base text, you pass it through a software known as a compiler, in this case a COBOL compiler, which converts each command into an equivalent machine code. And this is the machine code which ultimately runs on the system and they're doing the payroll processing for you. Now, while these have been extremely popular in today's time where you need interactive dialogue style of interaction with the computer, these languages are clearly not suitable because they are suitable for batch processing like payroll, for example. Therefore, you evolved into what are known as fourth generation languages, which are more interactive, which are non-procedural in nature, which is where you type a request and you expect a response. One of the best examples of a language of this kind is SQL, which is structured query language, typically associated with all database management systems. So in a database management system, once you have stored the data, you can, for example, if I'm looking for a list of employees who earn more than 5,000 rupees in salary, I can simply type a SQL query or the form, select name from the employee master where salary exceeds 5,000 or greater than 5,000, and I put a semicolon and the command executes. Immediately I get a list from the database, a list of employees where salaries exceed 5,000. Now that's the kind of interactive facility which we are really looking for in today's world. These are what are known as specification oriented languages or fourth generation languages. All that I have told the machine is, please give me a list of people who are above 5,000. I have not told it where it is stored, how to access it, how to process it, etc. I have just made a specification of what I need. How to get it is a matter of the system's intelligence to provide it to me. And therefore, these are non-procedural languages or specification-oriented languages. A huge leap forward compared to the third generation languages. And lastly, the advances in technology, particularly with the fifth generation Japanese project, which was towards artificial intelligence, robotics, etc., led to the discovery of a whole lot of natural languages. For example, you can speak to the machine. For example, you can signal. You have gesture-based games. You get Wii, for example, where you can do a hand movement and expect the game to respond. Now, these are all examples of natural language processing. With that, we come to the end of chapter 6, which is the operating systems. Thank you for joining me.